Okay, we're going to move on to our second talk in this first afternoon session. Sandra is going to talk to us about managing performance parameters with systemd. Please give Sandra a warm welcome.
Good afternoon, everybody. My name is Sander van Vugt, that's how I pronounce it. I'm from the Netherlands, flew in yesterday. Happy to be back at the LCA sysadmin miniconf. This is my slides. I'll make sure that by the end of the session you get a hold of it. As you can see, it's basically notes to myself. I don't like presenting with slides too much. In the Netherlands, I'm working as a technical instructor, and I write books and author video courses as well. And one of the items I've done a lot is Linux performance optimization. And well, with the arrival of systemd, that has changed quite a lot. And in the beginning, I considered that quite shocking, and then I dove into it to figure out how it works. And I think I more or less understand what's happening now. So the basics about systemd performance is that in systemd you have these unit files, and you can put performance-related parameters within the unit files. And I'm going to run a demo, and in this demo I'm going to show you what is happening and how you should do that. For this demo I'm going to focus on CPU shares. CPU shares is just one performance parameter, but once you understand how CPU shares performance parameter is behaving, then I think you'll be good and you'll be fine to configure it for any other performance parameter as well. I will also give you some hints on how to find the available performance parameters. And in the end, that helps you creating an environment where an application that is started by a systemd unit file will really behave like a container or a virtual machine, and will have dedicated performance resources. And that is also one of the reasons why I wanted to present this. I think systemd performance tuning is pretty cool. For this talk, I assume that everybody has at least a slight understanding of systemd, and you may have worked with systemd already. This is what's happening when I'm talking too much. Sorry for that. So to start with, I need to explain about slices. In the systemd environment, there are three different slices, and that's the user slice, the system slice, and the machine slice. Slices, consider it as slices of a pizza, which means that your operating system is divided into three equal parts. And all of these three equal parts have equal access to performance-related resources, which is what I want to show you in my first demo. So here we go to my demo virtual machine. My demo virtual machine is CentOS 7.3 virtual machine. This demo should run on other Linux distributions as well, but I'm doing a lot with CentOS. That's why I prepared it there. So to start with, I'm going to create unit files. Let me go to user lib systemd system. And if I'm doing that without typos, it might work so much better. And if you do a grep once on star, redirect everything that we don't want to see. If I do that without typo, it might run so much better. Sorry, it's still early in my time zone. We can see that there's an example unit file, which is fstrim. And this fstrim, in fact, it's not really the timer that I wanted, it's the service that I wanted. This fstrim is showing me the syntax that I need to create my own minimal unit file. I want to create a unit file. A unit file is like a service startup script in systemd. And in this unit file, I want to configure a task to run. And this task that I'm going to run is going to get some resources allocated to it. So what I need in this unit file is a line type equals one shot and exec start equals whatever I want to execute. So the one shot type allows you to run any command from systemd, which is pretty cool because it allows you to integrate anything in the startup sequence of a system. So what I'm going to do, I'm going to copy fstrim.service to etc systemd system, and I'm going to call it stress1.service. In systemd, the idea is that default unit files are in the You喚ll systemd system directory, and everything that is custom that you have created yourself will be copied to the etc systemd system directory. That is something relatively new to Linux, but it allows Linux to make a difference between everything that's provided from the packages and everything that is created by the system administrator. Oh dear, and I already have it. I forgot to remove the old one when I set up the demo, so it's removed now. So I'm going to edit this configuration file. And I'm going to keep the type equals one shot. And we are removing the exec start of fstrim because this is not fstrim. This is going to be a job that is creating a lot of work. dd if equals dev 0, of equals dev null. So that is a job that is going to copy nothing to nowhere, and it is going to do that endlessly. And that is exactly what I need. I need the system to be very busy. Also, I'm going to add CPU shares equals 1024. I like making typos this morning for some reason. So here we have CPU shares 1024. So CPU shares is a relative of a weight related to CPU shares that this script is going to get allocated. So what does the number 1024 mean? Well, it means nothing. It means nothing if it is just by itself. But the idea is that I can create 3 different scripts. And if in one script I'm using CPU shares 512, and in the other script I'm using 1024, and in the third script I'm using 2048, then it means that the first has half the amount of resources, the third has double the amount of resources as the second one, which has 1024. And in case you are wondering, could I do the same with 2, 4, and 8? Yes, absolutely, because again, this number allocated to the CPU shares doesn't really mean anything. Let me also show you stress2.service, which should still be around. Which is basically doing the same. So type is one shot, exec start is user bin dd, if equals dev 0, of equals dev null, CPU accounting is on. I included this line, which doesn't really have to be included, which is CPU accounting is on, which means that systemd is going to consider working with CPU shares. And in this case, we have CPU shares set to 2048. So that is double the amount of CPU shares. Now, before we are going to run this, sorry, let me use systemctl daemon reload to make sure that it considers the new unit files. Before we are going to run this, we need to talk a little bit about these slices. So we have a user slice, we have a system slice, and we have a machine slice. The user slice is the environment that is reserved for user-related jobs. The system slice is the environment that is reserved for operating system-related jobs. And then there's the machine slice, which is an optional slice that can be reserved to run virtual machines in a KVM environment, for example. The interesting thing about it is that the user slice, the system slice, and the machine slice, by default, will get a default number of CPU shares, which is set to 1024. And I will show you that something very strange is going to happen when we are going to run these jobs here. So let me start my first demo. And to make sure that I set the appropriate expectations, this demo is not going to give you what you are going to expect based on my story so far, because I need to do one more modifications. But I think that by doing a wrong demo to start with, you will better understand what is really happening. So I'm running systemctl start stress 1. Continuing it in the background. And let me run stress 2 as a background job as well. And now also, now I have started to systemd unit files, and these unit files are in the system slice. Apart from using the system slice, I also want to start a job in the user slice. So from my shell, I'm just going to run dd if equals dev0 of equals dev0, copying nothing to nowhere once more. My system will be rather busy with this, and that is exactly what I want it to do. Now let's see in top what is happening. Based on what we have seen so far, you should be able to predict what is happening, right? And the prediction would be, well, we have a user slice, we have a system slice, we don't use the machine slice here, and we have an equal amount of CPU shares in both slices. So the user job would get half of the available system resources, and the systemd jobs together would get the other half of the available resources. Let's have a look in top and see what is happening, and we can see, well, that's not exactly what is happening. Because we have 3 different DD jobs, 2 of them being the systemd unit files, and 1 of them being the user job that is running, and all of them are getting 100%. Now, do we have an obvious explanation for that? Anyone, any idea? Multiple CPUs, exactly. If I press 1 from my top interface, you can see that the system is currently allocated to work with 3 different CPUs. And if you are running 3 different CPUs, well, the story is getting different because any job can run on a complete CPU. So to make this a better demo, we are going to switch off some of the CPUs. This is one of these impossible parameters in the sys file system, sys devices system CPU. So if we get to sys devices system CPU, then we see that we have CPU 0, CPU 1, and CPU 2. And if we go to CPU 2, then there is this file with the name online. If we get what is in there, and then it currently has a 1. And if we echo 0 to this online file, let's just verify, and we do the same for CPU 1. Oops. Back to top. And we can immediately see the result. So the user job that is kind of funny. Something strange is happening here. Why does something like that always need to happen in a demo? Anyway, the user job is getting too much resources. Based on what I see here, I would say that the user slice has the CPU shares parameter set twice as high as the system slice right now. And the systemd job just has a 20 and 10, in which we also see the equal division between the CPU shares of 2048 and 1024. Let me just foreground the user job. Control-C it. And let's continue without the user job, where you can see how this relates to the two jobs that are still running in the system slice. Now, based on this system and user slice information, there is something very important that is following. Because what you can deduce from here is that anything that is running as a system job will get half of the CPU slices. Will get as many CPU slices as your user environment. So imagine that you are working on a server, and on your server you have some important real-time business going on. And you have configured some of your services with CPU shares to make sure that your Oracle database server gets 8 times the amount of CPU shares as the web server. And then there is this user getting in, and this user is starting a job that is going to keep your CPU completely busy. Then this one single user job, without any changes in the configuration, will get as much CPU shares as all of your system jobs together. And that is really something that you want to consider. Now, if you want to change that, that's possible because slices are configured in systemd as well. And you can see the slices configuration in user lib systemd system. You will find a user.slice, a system.slice, and a machine.slice. And you will be able to configure the appropriate amount of CPU shares within those slices. Right. So let me see what we have done so far. We have done so far up to item number 5. So we have seen that CPU shares are relevant in the user system and machine slice. We have done the demo with the stress scripts. And then we have run the user job, and in top we have seen that it doesn't work, and it didn't work because of the multiple CPUs. And we have also switched off some of these CPUs by touching the sys file system, and now we have seen that it does make sense. So there are some utilities that you can use to monitor what is happening related to systemd performance as well. And I want to have a quick look at these utilities. That is systemd cg top and cg list. There it is, systemd-c as cg top. And in CG top, CG top stands for C group top, because this is really a C group functionality that is implemented in systemd. If you have ever worked with a C group, as in control groups, in Linux distributions before systemd, systemd is just going to include all the parameters that you will find in the C groups as well. And here we can see related to these C group parameters what the different parts of the operating system are doing. So we can see a lot of activity in the system slice with a totality of 99%, and we can see the user slice with a totality of 0. A little bit percent, because nothing really is happening in the user slice. And we can also see that within this system environment, we have system slice stress2.surface. And within the user slice, we have, well, nothing really happening at all because I stopped everything. Apart from cg top, there is a cgls command, and cgls is going to give you the same information but from a different perspective. So this hierarchical overview is interesting as well, because this is showing relations between the different parts of the operating system that are currently running from a performance perspective. So within the user slice, very interesting, we have user0.slice, and within this user0.slice we have two scopes as well. Up to now I haven't touched upon the subject of scopes, but a scope is like a slice within a slice. But we don't call that a slice, we call it a scope to make it more manageable. And within this session 4.scope and the session 2.scope, we can see that there is some jobs that are running. Now this is interesting as well. If you do not change anything in the configuration, every scope will get the same amount of resources allocated to it as well, which ensures that one user within the user slice will have the same settings available as another user within the user slice. And if you go down the list, then you can see anything else that is happening and how this relates to the different performance-related parameters. Now, how do we find all these parameters that are available? I mean, in systemd you have these unit files, right? And these unit files allow you to run services, but also to set timers, which is like cron jobs, to mount file systems and so much more. And within these unit files, there is really a lot of parameters that can be included. If you wonder which parameters can be included, then I would suggest you have a look at systemctl show. So systemctl show stress1.service is going to consider the type of unit file that it finds in stress1.service. And it is going to show us the available parameters for stress1.service. And here we see a list of everything. This is not just related to systemd C group performance parameters. This is related to everything. And if you go down the list, then you can find some performance-related parameters. Like in here, CPU shares is 1024. That's what we've just said. Like in here, for example, memory limit. We haven't talked about memory limitation in this demo, but memory limitation is another parameter that you might want to include. It's a very useful parameter to make sure that memory resources are reserved for a specific service as well. So you want your Oracle database never to go beyond 8 gigabytes of RAM. This is where you specify it. Put it in anywhere where you want to do it. And then we can see some more detailed information that relate to this systemd C group parameters as well. If you browse down the list, you can find some other interesting parameters also, like the out-of-memory score adjust. If you have ever seen the out-of-memory killer becoming active, this is how you can manipulate that, or a default nice value, or you can set I/O scheduling, and so much more. So the command to figure out what is available is systemctl show. Just use systemctl show on any unit file that you might want to use, and you will figure out what is happening. Oops, this is a typo in my slides. I typed status. Status is not going to show that. Systemctl show is showing that. If you want more information about the C group parameters that can be included in systemd, there is a very nice man page. And the man page is systemd.resource-control. So let me show you systemd.resource-control, because it has some really interesting information as well. It's basically explaining everything that I've just shown you. So if you want to look up the documentation to figure out what is really possible, this is really where it's all starting. So it's explaining slices, it's explaining scopes, it's explaining surfaces, and most important, here we have the parameters that we have just considered, including this CPU shares. So CPU shares is weight is what we have done. CPU accounting. CPU accounting is a feature that is on by default. That is on CentOS. I cannot talk for all the other Linux distributions because I haven't worked with all of them, but normally you will find that CPU accounting is on. So this will work without any further preparation. If you are on a Linux distribution where you are trying to do this and you find that the CPU shares are not considered, make sure that you switch on CPU accounting. You can do that on a slice level, you can do that on a unit file level, basically any level that you want to do it. CPU quota is an interesting parameter as well. So that is a time quota that you can use to specify limitations. Memory accounting is what we have just considered. A memory limit is bytes. So if you want to impose a memory limit, put it in here. This is a very interesting parameter. It's also a very dangerous parameter because if you set a memory limit of, let's say, 1 megabyte for a process that needs 4 megabytes to start up, well, you can guess what is going to happen. The process will never start up. There is block I/O accounting as well. So if you want to manage I/O access, consider using block I/O accounting, including the block I/O weight parameter, which allows you to give one process much more I/O bandwidth as the other process. And there is a couple of more interesting parameters in here as well. So if you have ever worked with C groups in previous versions of Linux, well, that is Linux before systemd. What we have seen in my demo so far is that working with C groups has changed considerably in a systemd environment. Everything is going to the unit file, and to be honest, I like it that everything is in the unit file. Because if you have ever tried to reserve resources in a pre-systemd C group environment, well, with the CG red and the CG, what was the name of this other service? Again, I don't remember. It was a lot more complicated. So if you are still amongst those people that think that systemd is bad for Linux in general, well, I kind of like it, and this is one of the reasons that I do like it. And that is all I wanted to share with you today.
Okay, we've got a few minutes for questions, and then there's a short break before the next speaker. Does anyone have any questions?
Thanks. Do you know if C groups can be inherited by subprocessors? So can I set almost a container? I'm thinking, how well does it integrate with batch? They may be two separate questions.
I do know the first question, the answer to the first question, and the answer is yes. So subprocessors will automatically inherit the settings for the parent process. And the second question, does it integrate with what did you say?
With a batch schedule of any sort.
I'm not sure about that. I should have to look it up. So you have a question down there?
Hello.
Yes?
Cool. I was just wondering, the output of system control show all the numbers were really huge numbers, and on my machine exactly the same as yours. Are they hard-coded defaults, or where do those numbers come from?
I didn't hear you quite well, but are you saying that on your machine you don't see the different behavior as on my machine?
No, sorry. The output of system control show, all the limits and whatnot are very large numbers, are they just the defaults, or where do those numbers come from?
So your question, let me rephrase the question to make sure that I do understand it well. Your question is about systemctl show on /1.service or anything, and then you see these very large numbers like memory current. Are these just the defaults? Well, in fact, yes, they are. And it means that by default, there is no limitation at all, because this is all addressable memory. I haven't really looked at the parameter, but I would guess in Linux virtual memory as a total. So instead of seeing a -1, which is pretty common in Linux configuration files as well, in systemd you just see these huge parameters. Any other questions?
Hello, this is perhaps more a C group question than systemd, but do you know kernel processors, whether they can be allocated into C group slices to share resources with non-kernel processors, you know, like a ButterFS transaction worker, for example?
Can you rephrase the question, because I'm not sure how to...
So the question is about kernel processors. So for example, like a ButterFS transaction worker, can they be allocated into C groups, or are they sort of separate?
So that's a very interesting question, and the only honest answer is I have never looked at it. So anything I'm going to say is a guess, but as it is a kernel processes, and I don't see any unit files for kernel processes, I'm afraid that we won't have any integration there. But if anyone has a different opinion about it that's coming from experience, please share. Welcome.
Just one question over here. When you're running the top command, you're able to easily identify the user processes and the system processes, the different commands running. How did you see it just from looking at the output?
So your question is, when I was running the top command, I'm rephrasing the question a little bit to make sure that I understand it right. How come that I was able to identify the user processes and the system processes? Because top doesn't say from which slice a command is coming. To be honest, that is correct. Top does not include the information about that. I would need systemd cg top and systemd cg ls, these two commands that I've shown you by the end of my presentation, to be sure. In my top demo, well, I was kind of cheating, and based on experience, I was able to tell you this is user and this is system slice. But yes, you are right, this information is not included in top. Yeah, that's not a way of guessing it. There are different ways of guessing it from top. That's exactly right. Yes.
Okay, we'll need to wrap up the questions now. Please join me in thanking Sander.